Topic 17D. Acceleration of reaction rates. In the lab and in life, it can be useful to make a chemical reaction go faster, and there are a few different ways in which this can be done. One of the simplest ways is to simply increase the temperature of the reaction that's being run. In general, reactions will run faster if the temperature is increased. Another way of increasing the rate is to use a catalyst. A catalyst, such as that shown here in this elephant toothpaste reaction, gives rise to a very rapid reaction. It's also possible to increase the rate of chemical reactions that are heterogeneous or involve solid phase reactants. The rate of a solid phase reaction generally increases if we increase the surface area that's available for the reaction. Let's return back to this relationship between reaction rates and temperature. A relationship between the natural logarithm of a reaction rate constant and the inverse temperature could be observed for many reactions, and this observation was originally made by Arrhenius. Arrhenius described this with this equation known as the Arrhenius equation, where the natural logarithm of the rate constant K is equal to the natural logarithm of a constant minus an energy term divided by RT. This energy term is what's known as the activation energy, whereas this constant A is referred to as their frequency factor. If we rearrange this equation, we can appreciate the exponential relationship between the size of that activation energy and the speed of the reaction, where a larger activation energy gives rise to a smaller rate constant or a slower reaction. Now, this linear relationship between the natural logarithm of the rate constant and the inverse temperature can be visualized by plotting these two variables. And so for any chemical reaction that follows this behavior, if you were to plot the natural logarithm of the rate constant as a function of 1 over t, you should see a linear relationship. The slope of this line is given by the Arrhenius equation, which happens to be equal to the negative activation energy divided by R, where R is the gas constant. Like any linear equation, the slope is also equal to the change in the y variable divided by the change in the x variable, where in this case our y variable is the natural logarithm of the rate constant and the x variable is the inverse temperature. If we take any 2 points on this line and calculate this difference in y divided by this difference in x, this is a way of getting the slope, which we know is equal to the activation energy divided by R. We can rearrange this expression to give us a straightforward equation that we can use to calculate the activation energy given two different rate constants acquired at two different temperatures. This is an equation that's actually similar in form to another equation that we have previously encountered, known as the Van 't Hoff equation, where instead of rate constants, we are looking at equilibrium constants. Instead of activation energy, we would have the change in enthalpy for the reaction. The Arrhenius equation gives us a way to characterize the rates of chemical reactions. So if we look at an example of a hydroxide ion reacting with methyl bromide to form methanol and a bromide ion, in this particular reaction, the hydroxide ion approaches that carbon center and at some point will start to form a bond with that carbon, while at the same time the leaving group, which is the bromide, will start to dissociate, giving rise to a high energy state, which we call the transition state, where we have partial bond formation between the hydroxide and the bromide to that carbon center. If we were to look at the energy of our reacting species as we go through this reaction coordinate, we should see an increase in the energy until we reach a maximum, whereupon it decreases until product formation is finished. This highest energy point on the reaction coordinate corresponds to this transition state, and in order for the reaction to go forward, our reacting species must have enough energy to overcome this energy barrier. So Arrhenius parameters do have some physical meaning, and we can look at the entire exponential term e to the power of minus Ea over RT, and this corresponds to the fraction of collisions that have an energy that's larger than the activation energy. This pre-exponential factor A, is also called the frequency factor, is another characteristic of a chemical reaction, and it depends in part on the frequency of collisions. In fact, there are a lot of physical parameters that go into the frequency factor, and these can be conceptualized in a simple theory known as the collision theory. In this theory, we assume that molecules must collide with sufficient energy in order for the reaction to occur. However, we can have a number of collisions with a total kinetic energy that's greater than the activation energy and not necessarily give rise to products. And this reflects the fact that some fraction of collisions will depend on things like the orientation and the size of the colliding molecules. So imagine we have molecules that are colliding, but not in the correct orientation. We can see that after the collision, nothing happens and they simply diffuse in the opposite direction. However, if the two reactants happen to collide with the appropriate orientation, we can imagine that bond formation is allowed to occur and that this gives rise to product formation. And the fraction of collisions that gives rise to product formation is reflected in the frequency factor A. Now, in collision theory, the frequency factor is proportional to a number of physical parameters of the molecules that participate in the reaction. You can see in this proportionality that we have a variable P, which is called the steric requirement. And this reflects the complexity of the reaction. The more complicated the molecule, and therefore the more limited the range of orientations that would give rise to a product are, the slower the reaction rate will be. In addition, this factor sigma reflects the cross-sectional area of the molecule. So larger molecules will have a larger potential reacting surface, which should increase the proportion of collisions that give rise to a product. So according to the equation that's derived from collision theory, the rate of a collision will increase with the square root of the temperature. The collision rate will also increase with an increase in size of the molecule that's reflected in the cross-sectional area, and will decrease with the square root of the mass due to this inverse proportionality between the rate constant and the square root of the molecular weight of the molecule. One more way that we could consider for accelerating a chemical reaction is to use a catalyst. A catalyst is defined as a substance that can make the reaction go faster without being consumed itself. And its ability to do so depends on its ability to decrease the activation energy compared to the uncatalyzed reactions. Catalyst does not change the difference in energy between reactant and product. This is an important feature of the catalyst. How can a catalyst decrease the activation barrier? Let's go back to our reaction of hydroxide with methyl bromide that goes through this transition state that has a partial negative charge on both oxygen and bromine atoms. Suppose this is the transition state that we want to stabilize with partial bond formation between the nucleophile and the leaving group. One way to do so would be to provide a hydrogen bond to counter the negative charge that's accumulated in the transition state. So this neutralization of the partial negative charge should have a stabilizing effect on the transition state and decrease the activation energy. There are in fact many different ways in which one could imagine this reaction could be accelerated, but this is simply one example. In this section, we have examined how reaction rates can be increased and used the Arrhenius equation to find the activation energy as well as the reaction rate at different temperatures. We've also looked at how collision theory can be used to explain why reactions go faster at higher temperatures and the effect of molecular size and mass on reaction rates. We've also briefly covered how reactions can be catalyzed, and we'll learn more about how enzymes can do this in biological systems in our next section.